Hello everyone. In this video clip, I'm going to go over 3 sections of our textbook, 4.3, 4.4, and 4.5. So basically, in those 3 sections, we'll be talking about 2 things. The L'Hopital rules for limit and how to sketch a curve using the properties of derivative. So let me start with the L'Hopital rules. This is in section 4.4. And the 4.3 and 4.5 is about sketching a curve. Okay? So L'Hopital rule. Basically, I say this. Say you have a limit of a fraction, say f of x over g of x. When x approaches some number a. Keep in mind right here, I write a in general, but a could be a specific number, could be positive infinity, could be negative infinity. All right, and somehow your limit when x approaches a, it looks like infinity over infinity or 0 over 0. Okay, and by saying infinity and over infinity right here, I'm including positive or negative infinity. All right, of 2 forms, either infinity over infinity or 0 over 0. Then the L'Hopital rule said this: if the limit this way, then this limit of f of x over g of x will be equal to the limit of f prime of x over g prime of x, and x approaches a. In other words, you take the limit and just say this is of the form infinity over infinity or 0 over 0. I'm sorry, it's derivative right here. Then you can take the limit of the derivative of the numerator over the derivative of the denominator. Okay? And hopefully the second limit right here will be easier. For example, recall something that you guys seen before. Limit of sine x over x when x approaches 0. Alright, so this is a fraction. When x approaches 0, sine of 0 is 0. And x approaches 0, so this is of the form 0 over 0. Okay, so we can use the L'Hopital rule in here. My L'Hopital rule, let me write this way. So by L'Hopital rule, this limit is going to be equal to the limit of what? The derivative of sine of x is cosine of x. The derivative of x is 1. X approaches 0. Okay? And this is just limit of cosine of x. X approaches 0. And cosine of 0 is 1. This limit is 1. We have a very handy limit that you guys are going to use a lot, which is limit of sine x over x when x approaches 0 is equal to 1. Okay? And the whole section 4.4 is about this. So it's all about practice. We only learn one thing here. You have a limit of a fraction. And if it's of the form infinity over infinity or 0 over 0, then you can use the derivative of the top over the derivative of the bottom to calculate the limit of that. Gonna be the same answer. Alright. Or the second useful one that you guys have been using previously was this one. Limit of 1 minus cosine of x over x when x approaches 0. You plug the next equals 0, cosine of 0 is 1. This is 1 minus 1. It's over 0. So 1 minus 1 over 0, which is 0 over 0 of the form 0 over 0. Then you can use L'Hopital rule again by L'Hopital. This limit is equal to what? The derivative of 1 is 0. The derivative of cosine is negative sign. With negative become positive. Sine x over 1. The derivative of x is 1. And x approaches 0. So sine of 0 is 0 over 1. Sine of 0 is 0 over 1 is 0. Okay, so far, so good. Or you can use a lot of examples. Let me just look at the exercises in the book and then show you guys a couple more examples. And we're going to move on to the second item. This is 4.4. Okay, how about this? I see this. Limit of ln of x squared over, where was that? Over x. When x approaches infinity. Now you try x. Go to infinity, ln of infinity is infinity. Infinity squared is infinity. And this is of the form, of course, is a form of infinity over infinity. Okay, so it looks good, so we can use a L'Hopital rule. So by L'Hopital, let me put the L right here, by the way. This letter L stand for L'Hopital, okay? By L'Hopital, this limit gonna be equal to the limit when x go to infinity, the root of ln squared. I have to use the chain rule in here, bring the 2 down, ln of x, and then times the root of ln of x, which is 1 over x, and everything divided by 1. You guys see where I got the 1 from? The root of x is 1. So this is limit of 2 ln of x over x when x goes to infinity. Now what? L'Hopital rule again. Why? When x goes to infinity, this is ln of infinity, which is infinity. So twice of infinity is still infinity, over infinity. So this is still of the form infinity over infinity. I'm going to use L'Hopital again. This is equal to the limit when x goes to infinity. 2 ln of x, the root is 2 times 1 over x. And then the root of x is 1. So this is just 2 over x, right? Limit of 2 over x. X goes to infinity. X goes to infinity, so 2 over infinity is 0. That would be the answer. Okay? So in this example, I'm actually using the L'Hopital rule twice. And we have no limitation of how many times we're going to use L'Hopital rule. If it matches the categories, infinity over infinity or 0 over 0, you are okay to use L'Hopital rule. Okay, so let me look for another type of problem. This is a tricky one. For another example, see something like this. Try this. Limit how about this? X raised to the power of square root of x when x approaches 0 plus. X go to 0 plus. Okay, we have to go 0 plus because square root of x cannot be negative until a real number. So make sure that everything makes sense. All right, we have a problem here. You see x, the variable x is on the base. X is also the exponent. And we cannot work with variable on both base and exponent at the same time. So somehow, we try to bring the exponent down. And the greatest tool, I think, to bring the exponent down is apply the log on both sides. So instead of calculating this limit, I'm going to look at log of log of limit, log of the limit of x raised to the power of square root of x when x approaches 0 plus. Okay. And one thing about this, we can interchange the log and the limit. Log of the limit is going to be the same as the limit of the log in this case. So it's equal to limit of course, x goes to 0 plus, right? Limit of the ln of x to the power of the square root of x. So this step is very crucial. See what we've done? I want to calculate this limit. I don't know what it is. What did I do? I applied the log on that limit. So ln of that log equal to the log ln of the limit. Let me take it back. ln of the limit equal to the limit of the ln. Okay? Now, what can I do with the ln? For the log, we can bring the exponent down. So this is equal to limit x approaches 0 plus of square root of x times ln of x. Okay? So far, so good. So we have product in here. And you don't see any fraction yet. So your question should be, how can I apply the L'Hopital rule in here? So let's see. When x goes to 0, what happened in here? Square root go to 0, right? Ln of 0 go to the log function looks like, what was the log function? Exponential function this way, so the log function is going to be this. So when x approaches 0 plus, ln goes to 0 go to negative infinity. Okay, so this infinity, this 0. So watch me see how I modify this, make it look like a fraction. This is the same thing as, oh, I still have room, so let me continue writing. Limit x approaches 0 plus, okay, and watch me. This is ln of x divided by 1 over square root of x. See? Divide by a fraction means multiply by its reciprocal. So this one and this one is the same. See? Square root of x times ln of x is the same as ln of x divided by 1 over square root of x, because when I divide it by the reciprocal, I multiply by square root of x. Okay? I have this. Now, it looks like fraction. Okay, let me rewrite a little. I'm going to change the radical sign into the exponential. So this is limit ln of x over x to the negative 1/2. Square root is exponent 1/2 is on the denominator, so negative 1/2. X go to 0 plus. Check it out. When x go to 0 plus, ln of x is going to be negative infinity. X go to 0, square root of x is going to go to 0, so 1 go to 0, go to infinity. So this is of the form of negative infinity over positive infinity. Alright? And again, of the form infinity over infinity, we are good to use the L'Hopital rule. Okay, so I wrote too big, so let me go up here and now continue the problem. I have limit x go to 0 plus of ln of x over x to the negative 1/2. Of course, L'Hopital, because of the form infinity over infinity. I'll put an L right here to indicate that I'm using L'Hopital. So limit x go to 0 plus. Derivative ln is 1 over x. Derivative of x to negative 1/2 is negative 1/2 x to the negative 3/2. Okay. You see, take negative 1/2 in front and then negative 1/2 minus 1, negative 3/2. So this is limit, okay, negative 1/2 at the bottom becomes negative 2 on top, and then x down the bottom, 1 3/2 on top. So x down here, x to the 3/2 in here is the same thing as limit negative 2 x to the 1/2. X go to 0 plus. X go to 0 plus. Okay, that x cancels out 1x, I got 1/2 left. And x go to 0, this is square root of 0, which is 0, but this is equal to 0. Alright, we haven't got the answer yet. What we calculate is this. The ln of the limit is equal to 0. So all we have is right here. Oh boy, I need some room to write. Let me write right here. ln of the limit, see? All the calculation all the way to here is just calculate what? ln of the limit. ln of the limit of x to the square root of x. X go to 0 plus is equal to 0. So how do you calculate that limit? Go back. ln, it means what? Log base e of something equal to 0. That means limit of x to the square root of x equal to e to the 0, which is equal to 1. I'm using a definition or log right here, guys. Log base a of, say, x equal to y. That means a to the y is equal to x. Applying to this from log base e of the mass rate equal to 0, so e greater than 0, equal to whatever inside, which is the which is the limit that we're talking about. And the limit is equal to 1. And this example is very typical for this type of problem. Whenever you guys have both variables, the variable on both base and exponent, the way that you're going to tackle the problem is applying the log on both sides. Of course, ln is the best log with base e that you can think of. And you calculate the limit of the log, and which is equal to the log of the limit, and then you take e raised to whatever you got, you have the answer. Okay. And via this example, I also show you guys another technique right here. What you see inside the log is what? Square root of x times L of x, which is no way it's a fraction at all. And you want to make this becomes fraction. See the way I changed it? Square root of x, L of x becomes ln of x over 1 over square root, reciprocal of square root of x. Now it is a fraction, okay? And they satisfy the condition for L'Hopital rule. And you guys can use L'Hopital rule to get to the answer. And keep those with you. We have like 4 or 5, I think 6 problems of this type in our textbook, and I assigned some for you guys in the homework. So use this example as a model. You can try practice and get your homework done. Of course, any question, please feel free to ask. Now, let me move on to the other 2 sections. Our textbook today will talk about 4.3 and 4.5. And the 3 sections, the 2 sections, 4.3 and 4.5, basically, we're talking about how to roughly sketch a curve using our knowledge of derivative. And say you have a function f of x. You guys know that f prime of x is telling you the slope of the tangent line, right? Slope of the line. So slope of the line. We have a couple cases. If f prime is positive, that means the slope tangent line is positive. It means what? The line positive going up. It means what? The graph tends to go up. Or another way, the function is increasing. And similarly, if f prime is negative, that means the slope tangent line is a negative number. It means the line's going down. It means the graph tends to go down. So the function is decreasing. And what if f prime is equal to 0? Means what? The tangent line is the horizontal line. Okay? And usually, how do I write this? That point gonna be local max or local min. Let me draw it this way. So this is the graph, right? This function going up, the function is going down. That point, the tangent line will be 0. F prime here equal to 0 means what? It's gonna be a local max. Or if the graph is this way, the graph tends to go down and then to go up. This point right here is gonna be a local mean when the derivative equals to 0. So that gives us a hint. Whenever you want to look for a local max or local mean on the function, you take the derivative of the function and set the derivative equal to 0. You'll find a point. Those point called the critical point. And usually the critical point may be a local max, maybe a local min, maybe neither. Who knows? Okay? But if it's a local max or local mean, for sure the derivative is equal to 0, not vice versa. Okay? That was on 4.3, and actually what we're telling you right here called the first derivative test. So let me show you the way I learned it when we talk about the first derivative test instead of writing it all out. This way. Let me give you an example. Something that we all know. Okay? How about f of x equal to 4x cubed minus, how about 3x squared? Okay? You see, this is a polynomial of degree 3. Actually, it's a cubic function. Leading coefficient positive, so I think the graph will look like this somehow. And let me try to show you that, try to convince you guys that I can use calculus to roughly sketch a graph that way. Okay, so whenever you have a function, the first thing that you have to care about is look for the domain of it. What is the domain of this function? Polynomial. Domain is what? All real numbers. The domain is from negative infinity to positive infinity. No restriction, okay? Of course, later on you study other functions that may have different domains. But in this case, in this example, it's all real numbers. This is the domain. Okay. Now I'm gonna study the fancy words for it is monotonicity, which is what? Increasing, decreasing of a function. So I'm gonna do derivative, f prime of x. What is f prime of x? It's 12x squared minus 6x. You guys see where I got that number from? Derivative, this one bring the 3 down, so 4 times 3 is 12. X cubed become x squared. Same thing here, 2 down, 6. 3 times 2 is 6, and then x. Alright, now you're going to set f prime equal to 0. F prime of x equal to 0. So you have, this is what? Factor out of 6x. I got what? 2x minus 1, right? Go to 6x times 2x minus 1. So either x equal to 0 or x equal to 1/2. Those points that you have for f prime equal to 0, we call them the critical values or critical point. Critical values. Critical points. All right. Those could be those are the potential maximum or minimum, or I mean local max, local min, or maybe just the junction point. All right. Now, this is how we have the first derivative test. The way I show you guys is going to be a little bit different from the book, but I think it's pretty effective, so I'll show you. All right. We have x, right? Domain is from negative infinity all the way to positive infinity. And then we have f prime of x. And, oh, in short, just write f prime is good. And then we got f of x, okay? We're going to list all the critical points, critical values under domain increasingly. So we have 0 and then 1/2, okay? And we know that when x equal to 0, f prime is 0. X equal to 1/2, plug it in 1/2, f prime derivative is also 0. We just solve it right here. All right, now we're going to study about the sign of those. Recall in the very first week of our class, I gave you the sign table, review of the sign table. All right, so plug in something less than 0, say -1. Negative number, this is a negative number, this is another negative number, brought up two negative numbers, you got a positive number. What does that mean? It means that when you plug in any value of x from negative infinity to 0, f prime will be a positive number. And what does it mean by positive number for f prime? The function is increasing. Okay? And try something between 0 to 1/2 for x. Say x equal to 1/4, 1/4. So 2 times 1/4 is 1/2, minus 1 is going to be negative. Negative times positive is going to be a negative number. Try something bigger than 1/2, say 1, it's going to be a positive number. So, let's tell you what. F prime will be positive x from negative infinity to 0. F prime will be negative with x from 0 to 1/2. And F prime will be positive again when x is 1/2 or all the way to positive infinity. And that tells us something about the function f. It's going to be increasing, that's what we learned before. F prime is positive, increasing. F prime is negative, the graph is decreasing, and then back increasing. See? Even though I still don't have the precise graph yet, but I can roughly sketch a graph. It's going to look like this thing. Up, down, up. Okay? And with that much information, I can tell you what. We're going to have a local maximum right here, which is the point that we're talking about right here. And we're going to have a local minimum. So I know that we have a local max at x equal to 0. And we have a local mean at x equal to 1/2. And not done yet. Can you calculate a local max or local mean? That's not hard. X equal to 0, look in. Calculate f of 0. Increases. Then f of 0 is going to be the local max. How much? Look in 0, 0 here, 0 here, so 0. And the local mean at x equal to 1/2, all right? And how do you find this point right here? How low is that point? You plug in x equal to 1/2. So f of 1/2 is equal to 4 times 1/2 cubed minus 3 times 1/2 squared. So 1/2 cubed is 1/8 times 4 is 1/2. And then this is 1/4 times 3 is 3 over 4. So the answer is negative 2 over 4, which is negative 1/2. All right. So maximum right here is at equals 0, y 0, so the graph is going to be like this. Okay, and this is what? 1/2, negative 1/2 y x. Right, so the graph will look like that. Okay, so what we've seen in here is the first derivative test. I'm going to tell you the critical values of critical points and the critical points of the potential local max or local mean. Could be neither. We use a sign table, the sign of first derivative. That's why they got the first derivative test. Positive, graph go up. Negative, the graph go down. Positive, the graph go up again. And by looking at the shape, we can at least roughly determine where we have a local max or local mean. Okay? All right. Now, we're going to learn another thing, something called concavity. Okay? So let me go back to our graph. It looks like this. Cut up, right? We have two portions right here. The first part from here to here, we say that the graph is concave down. The second half of the graph from here to here, we say that the graph is concave up. Well, make it easy for you guys to figure it out. Concave down means what? You choose any point on that portion and you connect those 2 points, you have a line segment. That line segment is below the graph, and that point concave down. And vice versa. This point right here, we have 2 points. We connect 2 points on that portion, and we have two on the curve, and you have the line segments above the curve. So it's concave up. So my little trick to remember, concave up. Okay? Up. And of course, the other one is concave down. Okay. There are some graphs always concave up, like parabola. Okay? With a positive coefficient, or always concave down. Never change. This cubic one, half of the graph is concave down, another half is concave up. This is a point of change in the concavity. This is, we call it the point of inflection. Point of inflection is a point of change in the concavity. All right? And how do we know whether the whether the graph is concave up or concave down? How do we know the concavity of the graph? This is another test called the second derivative test. This one right here, by the way, got the first derivative test. Now we are talking about the second derivative test, but it's the same idea pretty much. Second derivative test. You have f double prime, right? Second derivative. If f double prime is positive, the graph is concave up. F double prime is negative, concave down. Okay? And then what if f double prime is equal to 0? We have a point of inflection. Possible. Okay. So far, so good. So let me continue on this example then. I'm going to show you everything, right? Not just monotonicity, increasing, decreasing, but also talking about concavity in here. So I got domain is negative infinity to positive infinity. F prime of x is 12x squared minus 6x, right? And then we have two critical value, critical point, however you call it. X equal to 0.